Let's do an example of a second class lever calculation. I'm going to once again read the problem to you here. A wheelbarrow is used to lift a 150-pound load. The length from the wheel axis to the center of the load is 3 feet. The length from the wheel and the axle to the effort is 7 feet. Let's first start out by drawing a picture, and this is how the picture is going to be for every second class lever. Have the fulcrum and the lever. Second class lever, the force of the resistance is in the middle. Middle not meaning midpoint, but just between the ends. And then the force of the effort is going to be on the other end. And then we have to include in this the distance of the resistance, which goes from the resistance to the fulcrum, and then the distance of the effort, which goes from the effort to the fulcrum. This is how every second class lever picture is going to look. So let's write down each of these variables. We got the force of the resistance, we have the distance of the resistance, we have the force of the effort, and we have the distance of the effort. Let me read this problem again. It says that the wheelbarrow is used to lift a 150-pound load. The resistance, therefore, is 150 pounds. Continues to say the length from the wheel axis to the center of the load. That's the distance of the resistance. It says that is 3 feet. The length from the wheel and axle to the effort, so the distance of the effort, is 7 feet. So, define your variables, which is what we've done up here. We didn't define them, but we said what the numbers represented with the letters. And then draw your picture, which we did. We illustrated it and we annotated it. Let's say that the first question to this is to find the ideal mechanical advantage of the system. Find ideal mechanical advantage. Well, we're going to first start this by writing the formula for ideal mechanical advantage. You take the distance of the effort and divide by the distance of the resistance. Distance of our effort, we can see up here, 7 feet. Distance of our resistance is 3 feet. If you divide feet by feet, they cancel. Something divided by itself is 1. 7 divided by 3 is approximately 2.33. The ideal mechanical advantage of this is 2.33 to 1. Second question to the same problem. Using static equilibrium calculations, calculate the effort force. Notice that's the one force, the one variable that we don't have a number for, so it makes sense that they're going to ask for this. Calculate the effort force needed to overcome the resistance force in the system. So what it's basically saying is, what's the minimum effort needed to lift the end of the wheelbarrow, where your hands are going to be. Hands are going to be right here on this effort. So once we get this number, to make the system static, then that's the minimum force you would need to lift it up. I can fit this in here. So, once again, we take the moment of the resistance, and that must equal the moment of the effort. If those are equal, it's in static equilibrium. The moment of the resistance is calculated by taking the force of the resistance times the distance of the resistance. The effort moment is taken by calculating the force of the effort times the distance of the effort. We have numbers to plug in that we have up here in the top right hand corner. We have 150 pounds. Distance is 3 feet. Every number that you put into a formula must be labeled. If it's not labeled, then it is not correct. The force of the effort, we do not know. I'm just going to make that red to emphasize it. Distance of the effort is 7 feet. On the left, we can multiply 150 and 3 and get 450 foot-pounds. On the right, typically we put the numbers in front when they're being multiplied times variables, so we have 7 feet times the force of the effort. We're trying to get the force of the effort by itself. To do so, it's currently being attached to 7 feet by multiplication. Opposite of multiplication is division. So if we divide both sides by 7 feet, on the left we get 450 foot-pounds divided by 7 feet. On the right, we just get the force of the effort. On the left, you're dividing feet by feet. Anything divided by itself is 1, with the exception of 0. 450 divided by 7, so the nearest hundredth, is 64.29. The only label left is pounds, which makes sense because it's a force. So this question, once again, what's the minimum force needed to overcome the resistance? Well, the minimum force would be 64.29 pounds. If you had that much force, it would lift it off the ground, and it would be just wouldn't be going up or wouldn't be going down once it was attached to your hands. And then if you had any more pressure than that, any more effort, you'd lift it up. If you let go with a little bit of effort, then it would go back down.